let us finish our discussion of the heat equation. Let me remind you how we did it. Here is the boundary value problem. We have partial differential equation and two conditions. Step 1, we found infinitely many functions. By the way, here are the formulas for these functions. All these functions satisfy the boundary value problem. All these functions are solutions of this boundary value problem. Moreover, last time I showed that any their linear combination is a solution of the same boundary value problem. Next question is, how about the middle condition? To be more specific, is it possible to find numbers C1, C2, and so on, Cn, such that this satisfies not only boundary value problem number 2, but also the middle condition, means boundary value problem 1. By the way, observe that in the middle condition, t is equal to 0. And if t is equal to 0, then what is written here becomes this. So once again, question is it possible to find C1, C2, and so on, Cn, such that f of x is identically equal to this? Well, for some functions, it is possible. For example, for this function. However, if f of x is equal to, say, 1, it is impossible to find numbers C1, C2, and so on, Cn, such that 1 is equal to this. Fortunately, if instead of a finite sum, we consider an infinite sum, then the answer is yes. Please take a look first at this theorem that we already discussed. If f and f prime are piecewise continuous functions on this interval, and if x is not one of the endpoints and not a point of discontinuity, then this series converges to f of x. Unfortunately, this result does not allow us to solve this problem yet. And there are two reasons for that. Reason number 1, our function here is defined only on the interval between 0 and L. Recall that in order to apply the theorem, our function should be defined on the interval from negative L to L, not from 0 to L. Moreover, we include the endpoints. Reason number 2, here f of x should be written as an infinite linear combination of sines only. Over here, we have both sines and cosines. In addition, we have a0 over 2. In the next section, I'll show you how to fix both problems relatively easily. Please take a look at the following really simple idea. So, our function f is defined between 0 and L. Fine. Here's what we do next. Well, imagine that the graph of our function is this blue curve. Forget square root of x. We have some graph, some, say, continuous blue curve from 0 to, say, 3. Here is what we do next. Let us consider a new function, the graph of which is the following. On the right-hand side, the graph of our new function coincides with the graph of our originally given function f of x. On the left-hand side, we have some, say, continuous curve between negative L and 0. So the graph of our new function is the following. Some curve here, say continuous curve, and same as the original function on the right-hand side. Note that we can perfectly apply this theorem to our new function. And we will come up with some infinite series for this new function. According to this theorem, our series will converge to the new function, say, g of x at any point x, which is not one of the endpoints and not a point of discontinuity. Since this series converges to g of x on this interval, in particular, it will converge to the original function g of x on the interval between 0 and L. I'll repeat once again. We have some function which is defined between 0 and L only. Step 1, draw some graph on the left. Say continuous graph. Now, the new function g of x is defined between negative L and L. Apply this theorem to the new function g of x. By this theorem, our infinite series converges to g of x at any point strictly between negative L and L if x is a point where the function is continuous. In particular, our series will converge to the original function f of x, which is defined between 0 and L. Here is what we do next. Remember, we want to write our function as an infinite series on sines only. But here we have both sines and cosines. It is easy to fix this problem. Note that cosines disappear if all a's are equal to 0. But once again, let us go back to this picture. Note that we can draw whatever on the left-hand side. In particular, if we rotate the blue curve 180 degrees about the origin, we will get this. And the total graph will be the graph of an odd function. Let me remind you what are odd functions. Odd functions are functions such that you replace x by negative x and you get minus in front. Graphs of odd functions are symmetric with respect to the origin. Conclusion: if we rotate this curve 180 degrees about the origin, we will get this. Therefore, the graph of this new function is indeed symmetric with respect to the origin, which means this new function is odd. But now, let us go back to our formulas. Note that if this function is odd, since cosine is even, the whole product will be odd, because odd function times even function is odd function. And from calculus 1, we know that when we integrate an odd function over a symmetric interval, the whole integral is equal to 0. Just take a look at this picture. If we rotate this curve 180 degrees about the origin, we will get this. And now, if we consider any symmetric interval on the right and on the left, we will have congruent origins. But since on the right, the region is above the x-axis, and on the left, the region is below the x-axis, the whole integral is equal to 0. Let me put pieces together. In the heat equation, we have some function which is defined on the interval between 0 and L. Step 1. Consider a new function g of x, which is defined on the interval between negative L and L, and the graph of which is the following. On the right, the graph of g is same as the graph of f. In order to obtain the graph on the left, we rotate the right-hand side graph 180 degrees about the origin. The new function g will be odd. Since g is defined on the interval between negative L and L, we can apply this theorem. Moreover, since g is odd, all a's will be equal to 0. Therefore, all cosine terms will disappear, a0 over 2 will disappear. Therefore, we write our function f as an infinite linear combination of sines only. Very last thing, note that if f is odd, and since sine is also an odd function times odd function is even function. And note that the graph of an even function is symmetric with respect to the y-axis. Thanks to this, the second integral can be rewritten in the following way. Integral not from negative L to L, but from 0 to L. And then here, instead of 1 over L, we will get 2 over L. Because if we have a function, the graph of which is symmetric with respect to the y-axis, the right-hand side is equal to the left-hand side. Therefore, in order to find the total area, we just find the area of the right-hand side only, which is integral from 0 to L, and then multiply the whole thing by 2, which gives us 2 over L. It's exactly what is written here. Please take a look at this. Let f and f prime be piecewise continuous on the interval from 0 to L. Compute a_n's and b_n's. This function can be written as an infinite series in 2 different ways. We just discussed way number 2. This is an infinite series on sines only. However, the same function can be written as this: infinite series of cosines only plus a0 over 2. Here is y. Again, let us go back to this graph. We just discussed what happens if we create an odd function out of our original function. However, if we create an even function out of our original function, reflecting this graph above the y-axis, our new function will be even. And now, going back to our formulas, if f of x is even, then the product here is odd. And since we integrate over a symmetric interval, all these will be equal to 0. Therefore, all sines terms will disappear. What is left is a0 over 2 plus an infinite combination of cosines only. Moreover, since this and these are even functions, the product of two even functions is an even function. Therefore, integral from negative L to L of an even function can be rewritten as integral from 0 to L times 2. It's exactly how we come up with this formula, where a's are this. Very last thing, both series number 1 and series number 2 converge to f if x is not one of the endpoints and f is continuous at x. It converges to this if x is not one of the endpoints and f is discontinuous at x. Lastly, if x is either 0 or L, this series converges to f of x. This series converges to 0. Folks, now questions.
So the two series are equal only inside the interval but not at the endpoints?
Yes, very good point. So series number 1 converges to f of x if x is 0 or L. Series number 2 converges to 0. Therefore, if f at 0 is not equal to 0 and f of L is not equal to 0, these two series converge to different points at 0 and L.
Makes sense.
Other questions?
Professor, is there any benefit in modeling our equation with cosines or with sines?
Well, look, it all depends on what you need. In our specific problem, we have to write it as an infinite linear combination of sines. There is no escape because formulas for use are these. There are no cosines here. We have only sines and e's. E's disappear because in the middle condition t is equal to 0. So we have this. Middle condition of our problem is f of x is equal to c1 times sine of pi x over L plus c2 times sine 2 pi x over L, and so on. We do not have a choice here. But of course, in other problems, sometimes we need to write a function only in terms of cosines. It depends. Does this answer your question?
Yeah.
So let me remind you that according to theorem 3, any piecewise continuous function on this interval can be written as an infinite series in two different ways. Way number one, way number two. Let us discuss examples. So let us consider a very simple function. F of x is equal to 1. Expand f in a pure sine series over this interval. So we apply the theorem above. By this theorem, f of x is equal to this. Note that since L is equal to pi, we replace L by pi and then cancel out pi. Done. We have to find bn's. Again, by the same theorem, bn is equal to this. We replace f of x by 1, it's given. We replace L by pi, it's given. We cancel out pi, done. By calculus 1, antiderivative of sine nx is negative cosine nx over n. We plug in pi, done. We plug in 0, done. Note that cosine of 0 is 1, and according to our previous discussion, cosine of n pi is either positive 1 or negative 1. If n is even, it's 1. If n is odd, it's negative 1. Since 1 minus 1 is 0, bn is 0 if n is even. If n is odd, bn is 4 divided by n pi. We plug in these expressions into the formula and we get exactly what is written. Folks, any questions about example number 1?
I have a more general question.
Yes.
What is the significance of having two methods, an and bn, to get this series?
Well, once again, it all depends on our needs and our applications. The heat equation is not the only application of Fourier series. In this particular example, we need only an infinite series on sines. But in other applications or other theoretical questions, we might need a series on cosines only. Does this make sense?
Yes, thank you.
Other questions?
Just to make sure I understand, in this problem, you could have done it with cosines instead if you wanted to.
Absolutely. Please take a look at B.
Oh, okay.
And f in a pure cosine series. Now there are two approaches. Approach number 1, let us apply this formula. However, it is much easier to solve this problem observing that 1, f of x is 1, is equal to 2 over 2 plus zeros. Conclusion. If in this formula over here we set a0 is equal to 2, all other a's are equal to 0, we get what we need. F of x, which is 1, is equal to a0 over 2, because a0 is 2, plus this, where all a's here are equal to 0. Repeat once again. We solve this problem in two different ways. Way number 2, we apply the formulas. We get a0 is 2, an is 0. But even without applying these formulas, we can easily come up with this result. If we take a close look at this formula, in order to write f of x, which is 1, as this series, it is enough to set a0 is 2, all other a's are equal to 0. Folks, at home, you take a look at this example. So now basically same idea, just integration is more complicated. The function is e to x. A0 is not so hard to find. We just integrate e to x. However, for an, we have much more complicated formulas because in order to integrate this, we have to do integration by parts. It's all shown in Appendix 2. The author offers a different approach here, but you don't really need this method. Similarly, in the last problem, we have a piecewise function. We want to write it down in pure cosine series. So, since L is equal to 2, we replace this L by 2. Then, first we find A0. Here's the formula for A0. Note that in the general formula, we have cosine. But if n is equal to 0, cosine disappears because cosine of 0 is 1. So there is no cosine here. In order to integrate f of x, step 1, replace L by 2 because L is 2. Done. 2 over 2 is 1. Then we split this integral into two pieces. F of x is equal to 0 over this interval. F of x is equal to 1 over this interval. Therefore, here we replace f of x by 0, here f of x by 1. Integral of 0 disappears. Antiderivative of 1 is x. Plug in 2, plug in 1, a0 is 1. In order to find an where n is greater than 0, we replace L by 2 first. Done. We simplify. We split this integral into two pieces. We replace f of x by 0 here and f of x by 1 here. Integral of 0 is 0, disappears. By calculus 1, use substitution. Antiderivative of cosine of n pi x over 2 is 2 over n pi sine of n pi x over 2. We plug in 2 and 1, done. Cancel out 2 here. We just rewrite this as n pi over 2. Observe that sine of integer multiple of pi is 0. Talking about this portion, one can check that sine of n pi over 2 is 0 if n is even, and then plus minus 1 depending on parity of this number. We plug in these expressions into the original formula, done. And lastly, we conclude that our series converges to f of x at any point of continuity strictly inside the interval between 0 and 2. If x is equal to 1, it converges to 1/2. We can use either the theorem or just plugging in 1 into this formula, and we're done.